Yes, thank you. So I can hear that already, that you can hear me well. So as Andy said, yes, I work in post-quantum. So today I'm going to give you like an overview of what this means for me. And let's start with telling you what it is. Okay, so when we give the definition of post-quantum crypto, it's it's a crypto that is implemented on a classical computer, but it is resistant to attackers, even to attackers that have a large quantum computer. Okay, why do we make this distinction? Because the public key crypto that we have deployed today in the world is actually not resistant to attacks on a quantum computer, specifically because these problems, factorization and discrete log, they're the underlying problems of our current schemes, and for them we have what we call the Shor's algorithm, which is a quantum algorithm that runs in polynomial time. So this means that we need to replace all the public key crypto that we use. And so it is really about public key crypto. So I mean public encryption, right? Public encryption in public key crypto, it just means encrypting your key that you want to exchange. So key encapsulation mechanisms, CAMs. And then another big area there is the signatures. And there's some other things that we want to do, but we are very focused on these two for now. So on the side of symmetric crypto, well, the picture is a bit, it is less dramatic, the impact of quantum computers, right? We have this Grover's algorithm that runs has a quadratic speedup over the regular exhaustive search, but quadratic speedup means that you need to double the key sizes. So there is a easier, we don't need to replace anything. I do want to argue still that this is a problem for everyone. Because when you think about it like any infrastructure, it starts with the handshake, it starts with the exchange of a secret key. And so then if your handshake is compromised, then the entire, everything that follows is also compromised. So that is kind of like the usual pitch that you get for post-quantum crypto. I do want to give you an alternative view today, right, or to tell you what this means, what post-quantum crypto means for someone that works in the area. And to me, it really means it is a study of hard problems, okay? Because when you have a hard problem, you have a public key crypto system. And what I mean by hard is specifically computationally hard problems, okay? So problems for which the best known algorithms are exponential in time. Here I have some nice problems on the slide, so that they're not all problems that are used in crypto. So for instance, these that are with light blue are not used in crypto because it's not enough just to have a hard problem. You need specific properties. Here in red, you have the things that you know, factorization and discrete log, which are classical crypto. And then I also have some problems that are used in post-quantum cryptography, so that are hard even for a quantum computer. And so you might be thinking like, okay, what is so special about these problems that they are even for a quantum computer, right? Or at least this is what I was thinking before I go into this field. And I think the answer to that is really that quantum computers are not almighty. They're just know how to do very specific things very, very well. Okay, and one of the specific things that they know how to do is this period finding, and you have this period in the discrete log and the factorization problem, and so that's why you are able to break them. So in a sense, it is more like these two problems are very specific and not all of the others that are post-quantum, at least in my view. And it just so happens that we have built, all of the crypto that we have built until now is based on these two problems. Okay, and so, yeah, very unlucky coincidence, right? But now we need to replace everything. But when you go even deeper in the field, you understand that it's not a coincidence at all that we have based our crypto on these problems, because that very same structure that actually makes them vulnerable to Shor's attack, it also makes them very convenient for cryptography. The discrete log, for instance, is just amazing, right? It has very small public and secret keys compared to the security that you get for them. It's commutative, it gives you key exchange, it's hard on average, it comes with pairings. So it is all these are things that we have taken for granted until now. And it is very kind of hard to replace them now. So that is what we're doing every day, just looking at different problems, adding some structure to make them better, smaller, nicer. And then if the C of the structure gives you some attacks. Okay, so I did make the pitch of even beyond quantum computers, it is not a good idea to put all your eggs in one basket, especially if your basket hides a period finding problem. So that's what I'm going to do in this talk. I'm going to first tell you about what are these, what we call the 5 families of post-quantum crypto, just to give you an idea of what these mathematical structures are. And then I'm going to show you an example of a cryptographic design, because I keep repeating how a hard problem gives you a crypto system. Then I will kind of concretize this with an example. And then if we have time, I'll go a bit over the timeline of what we have been doing. Not so much the timeline, but just to give you an idea of where we are now in the timeline of standardization. Okay, so let's start first with the fun part, the different flavors of PQC. So maybe you have seen these 5 areas. It's usually like these different problems. We kind of categorize them a bit so that we know what we're working with. And the way that I will approach this is that for each of them, I will just tell you what the structures are, tell you about a hard problem in the area, and then I will tell you how you can brute force this problem. Okay, I won't have time to go into cryptanalysis concretely, but I do want to tell you how you brute force a problem, because I believe that if you know how to brute force a problem, you know what the problem is. We're going to start with something, something that you're very familiar with, hash-based cryptography. And yes, we are in public key crypto, but you're used to hashes from symmetric crypto, right? You have this hash function is this function that is supposed to mimic a pseudo-random function. It takes some arbitrary length input and it outputs something of fixed length, so what we call a hash, this end here. And you know the hard problem there is to find the pre-image of your hash, or not the only hard problem, but let's say the one that if you break this, you break everything. And that one is very easy to explain how to brute force. You just need to try for all of the combinations. And you can actually build signatures from hashes, and it is very nice because the security is very well understood. And one very nice thing about them is that these digital signature schemes that are built on hashes, they have only one security assumption, right? You only have the assumption that your hash function is secure. And all of the other schemes, they have some problem plus a hash function, because they do need to use a hash function in the protocol. So it is kind of an unbeatable argument in terms of the security. And as I said, yeah, you 2 to the n for brute forcing it. Then we have what we call multivariate cryptography. So multivariate stands for multivariate systems of equations, right? We have systems like the one here in the example, so a system of equations with some variables, and your goal is to find a solution to this system, right? Finding a solution is finding an assignment to all of these variables that kind of makes all of these equations equal to 0. And you know that this problem is very easy if it's a linear system, right? You have Gaussian elimination and you just find the solution. When you go up a degree, as soon as you have multiplication, the problem becomes very hard. So that is like a hard problem that we use. The way that you brute force it, it's the actual brute force that you're familiar with. So like the binary search tree, if your system is over the binary field, which this one it is, otherwise you generalize that. And the way that this works is that you give an assignment to all of your variables. So let's say first you assign them to 0, and then you evaluate all of your polynomials and see whether they all satisfy the requirement to be equal to 0. Here they don't because of the second one. So then you need to go back, give another assignment to the last variable that you did. Try that one. If it doesn't work, you go with another example. And then, so this actually kind of builds you like the depth first search in a binary search tree until eventually you find, oops, sorry, I missed the solution. Until eventually you find something that is a solution to the system, and then you have one. And the complexity of this exhaustive search is, of course, 2 to the n if n is the number of variables, or q to the n if you know you're over a bigger field. Okay. So then the next type of crypto we have is this code-based cryptography. Code-based comes from error-correcting codes. So it is a different field, right? But crypto has then stolen some ideas from it. So it is a field where, yeah, you need to kind of, you want to be able to correct errors that maybe happen on the transmission channel when you're sending messages or when you're receiving messages from a satellite or something. And then for this, we have error-correcting codes. This is what the code looks like. Let's say you have this what we call the parity check matrix, this H here, and then you say that some word, so some vector, is a code word if it is in the kernel of this H. Okay, so if you multiply H by your word, it gives you 0. That is a code word. Otherwise, it is not. It is outside your code. Okay, and then if it is not, it means it has some error, maybe a small error. So it means that it's not just a code word; it's code word plus some E. When I say small, I mean that the number of zeros in this vector are small, is small. So then we call that the Hamming weight. And then the way that we use this in crypto is that we intentionally add this noise to a code word, and then the hard problem would be to kind of decode this and recover the code word. So what happens is that, if you kind of rewrite this, you will see that because these are linear codes, and so you get 0 plus h times your error vector equals something. This something we call a syndrome, and it is kind of like how far your code word is from how far your word is from proper code word, and this is what gives us the hard problem. So what we call the syndrome decoding problem. If we are given, I will write it more visual like this because it's easier to see. So you are given this H, which is the matrix that describes your code. You are given this S, and you need to find an E, this vector here in the middle, that satisfies this equation. Plus, also it is of low Hamming weight, meaning it has very few non-zero elements in it. And let me tell you just briefly why this would be hard, because it doesn't look like it on the first look, right? If you just want to find some vector that satisfies this, well, this is easy. It is a linear problem, right? There are many solutions to this. So you can describe it algebraically, and it's going to be linear. But then there is a second constraint. That was the weight constraint, okay? You also want this to be of small weight. And so, finding an E that satisfies this is easy. Finding an E that satisfies the weight constraint is easy, but finding an E that satisfies both at the same time is hard, and this is what breaks the linearity. Okay, how can we brute force this? Well, if you think about what this means in terms of matrix multiplication, well, you see that here you multiply the first row with the E to get this first element here. Okay, so it means that only those columns that correspond to entries in E that are equal to 1, only those kind of matter in the multiplication. All of these other columns that I've left don't really matter. So kind of this S vector is equal to the sum of these columns, the columns that correspond to the non-zero coefficients here. Okay, so then to just find, since this is the case, to find your E vector, what you need to brute force is which columns are taken to sum up to S. And so then it means that you pick randomly columns until you do this. And what is the cost of choosing this combination of columns? Where it is n choose t, right? If I know that t is the number of columns I need to have, and there are n in total, this is what I need to, combinations that I need to try. Okay, so that is one problem in code-based. Now we go into lattice-based. So you see, lattices are these grid of points that you usually see around when you, and they give very nice pictures, so you might have seen them. More concretely, it is a discrete subgroup of your Euclidean space. And why do I say discrete? Well, here the dots that are on the picture are points on the lattice. It says discrete because it means that around every lattice point you have this ball of empty space that doesn't touch another lattice point. Or maybe it's easier to see it with the description of the basis. So if I tell you, well, a basis for a lattice is just some vectors, linearly independent vectors. So here I drew everything in the two-dimensional space. So let's say this is a basis for this lattice. Here this vector 4, 0, and here this 3, 5. I did approximately, but you can see. And then you say that a point on a lattice is any integer combination of this basis. Okay, so it has to be integer coefficients in the linear combination. So any point here that cannot be written as an integer combination of these two is not a point on the lattice. Okay, so that is a lattice. What is a hard problem there? Where, for instance, you have the closest vector problem, which is if I give you some point in the Euclidean space, so this point here, for instance, it is not a point on the lattice, find the lattice point that is closest to it. And here, this would be the solution. Okay. So I'm not necessarily going to brute force this, but I'm going to show you why this is hard. So for instance, if you have something that we call a good basis, this is like the blue one on the left. And it is good because, well, usually if it's short vectors that are very orthogonal to each other, that's something that is kind of like a good basis. Here, one way that you can solve this problem, let's say this is your target point here. One thing that you can do is first write this point in terms of your basis. Okay, so yeah, I've calculated here that this point is equal to minus 1.4 times the first vector plus 2.2 times the second one. And you can see immediately that it is not a lattice point, right? Because these are not integer coefficients. What we can do, because we want integer coefficient, well, let's say a first naive idea is what happens if I round this up? Will I get to a nice, and to this, will I get to the closest one? And here it was the case, yeah, you actually found the solution, the correct solution. If you do the same thing with a bed basis, so this kind of, yeah, describes the same lattice, but the vectors are not so orthogonal. If you do the same thing, I did it again with the combinations, I did the rounding, and then this gives me this point here, which is farther. And in a, more bigger, this is just two-dimensional, so it seems like an easy problem, but if you go to higher dimensional lattices, this really becomes hard. And going also from a bad basis to a good basis is also a hard problem, so that's why we can't kind of solve it. And finally, the fifth family that we have is this isogeny-based cryptography. And I'm going to try to make it, to show you something that you're more familiar with, so the elliptic curves, right? This is kind of like a picture of an elliptic curve that you have seen before. So it's an algebraic curve that we usually draw like this because that's kind of the shape that it has. And you have points on this curve, and you know that you can multiply points by some scalar and to get another point on the curve right here. And this is what gives you like the discrete log for the discrete log problem. That is a classical crypto problem, not post-quantum. Okay, so if you're familiar with this, I will try to make you look at this point, this scalar multiplication on points as a mapping, right? You're mapping a point on your curve to another point on the same curve. Okay, and these are the equations that for instance, describe this mapping of multiplying the point by 2. It doesn't matter what the formulas are, but you can see that it tells you where does x go in the other point and where does y go on the other point. So then an isogeny is going to also be a mapping, but just the only difference is that instead of going from a point on the curve to the point on the same curve, it goes from a point on the curve to a point on another curve. Okay. And yeah, like here in the photo, and then it is not bijective. You see, you have several points that go to a same one and so on, and it still has some formulas, albeit more complicated than the previous one, but it's still a mapping. Okay. And the hard problem here is if I give you these two elliptic curves, and you need to tell me what the isogeny between them is, so that's going to be the hard problem. To tell you how we brute force this problem, I need to tell you 3 more things about isogenies, 3 properties. So first, the degree. Okay, so the degree is some property of the isogeny that tells you how big it is. Okay, why does it tell you how big it is? Because the complexity of computing it, so not finding it, not a hard problem, but even just computing it, is linear in the degree. So if you have some exponential degree, then it's going to be very hard to do. But you also have these properties of second thing. The degrees multiply when you compose isogenies. And this is kind of a way for us to compute a big degree isogenies if it's a smooth degree. So here, if you need to compute an isogeny of degree d, and d is equal to, I don't know, some small primes multiplied together, then you can just compute first, yeah, an L1 isogeny, then another L1, depending on what this exponent is. So you can compute them all in order, and since the degrees multiply, eventually you will get to a d degree isogeny. A third thing you need to know to get to a brute force algorithm is that, yeah, from a curve E, I know that there are L+1 isogenies of degree L, okay, for L prime. Okay, so now you can see how we brute force it. If I give you this problem with, yeah, I'm giving you this curve E, I'm giving you this curve E prime. So then how do you find the isogeny? Well, you can start guessing, right? Here from E, you will have 3 options. You guess one of them. Then you have only 2 options because the third option is going back, actually, and so on and so on. So this is also like a binary tree, but just, yeah, I drew it the other way around. So you need to kind of, yeah, do all of these combinations, and here at the leaves, you just compare, is this my curve E prime or is it not? And the complexity of this is 2 to the E if that's the degree of the isogeny. Okay, so we're done with the schemes. You know, not the schemes, the primitives. You know a bit how they look like. I promised you that I will give you an example. So what I decided to give you today is this Fiat-Shamir construction, because it's kind of like a very easy and fun thing to understand. And the hard problem that I'm going to use here is, well, another hard problem. By the way, this is in code-based crypto, but you will not know why it is code-based today because I stripped away a lot of the details. But let's say we're working with this 3-tensor object, which is kind of just a cube, okay? This is a cube, and each entry in the cube contains some number, okay? And then you take this cube and you do a linear transformation on all sides. So it means that you do a linear transformation by this matrix here on the left, and I will show you permutations because that's something we can actually draw otherwise, but imagine that it is any linear combination. So A multiplies on the left, so it does permutations on the rows. Then B multiplies on the right, so it does a permutation on the columns. And then the third one, T, does permutations of this third dimension. Okay, and this gives you another cube, another 3-tensor object. And then the hard problem would be if I give you 2 objects like this that are equivalent, can you find what are these 3 matrices that brought me here? Can you find what is the mapping that brought me from one cube to the other? Okay, so that is our hard problem. The way that we will use this to build a signature scheme, concretely, first we will go through an identification scheme. Okay, so that just means that I will be able to prove my identity, and specifically I will prove that I know the secret. Okay, here the secret is this secret transformation A, B, and T, and the public key are these 2 groups. Okay, so I need to prove to someone that I know my secret, but I cannot reveal my secret, of course, because then you won't be able to reuse it. Okay, so what we do is first we do a commitment, or for Ozgun, commitment. So you, the commitment looks like you pick some random other map, some ephemeral map, and you go to another cube object here, and you commit to this object, to this 3-tensor. Okay, and then see, if you look at this, you see that you get a triangle. Okay, because here you have the mapping, your secret map. Here you have your ephemeral map, the one that you just came up with, and here you also know how this object. So your second tensor connects to your ephemeral tensor, because you can just follow this map the other way around. You can do the inverse of this, get here, and then compose it with your ephemeral map, and then you get this. Okay, so if you know the secret, you know all 3 of them. Okay, this is the triangle that we're working with. And the way that the scheme is going to work is, we have this prover and verifier scheme. And the secret key is this ABT, and your public key are these 2 tensors here, these 2 cubes. So as I said, first you commit, make up some ephemeral map, and you commit to it. Then the verifier will give you a challenge, which is either 0 or 1, and then you will give a response. What is the challenge? So the challenge is, if the verifier gives you 0, then you need to tell them what this map is, the ephemeral one. If they give you 1, you need to tell them what this other thing is. And as I said, this proves that you know the secret, because if you're able to answer to both, it means that, you can also derive the secret from this. Okay, so it kind of proves your identity. Why do we go through this, challenges, giving the one or the other? Well, you can try to think about how you can cheat. Okay, you can prepare for if you know in advance what the challenge is, right? If you know that the verifier is going to ask you for 0, then you just invent this, you do the protocol as normal, you invent this ephemeral thing, and you know it, you can send it. If you know that they're going to ask you the second one, you can also prepare, because you just prepare something from this cube to another one, wherever, and then you can also cheat. But you have a 1/2 possibility of cheating, and then we just repeat this protocol enough times so that we are convinced that the prover has a very low chance of cheating. Okay. And then from this, well, it's just an identification scheme, right? Our goal is a signature, so we make it interactive in a very simple manner, but a very clever transformation. Instead of using the prover to get the challenges, we just hash, okay? And specifically here, okay, same thing about the secret and public key. So we just hash the message and the commitment, and then that will give us the challenge. So if the first bit is 0, then it's challenge 0, otherwise it's 1. And we cannot control what the hash gives us, so like why the prover cannot cheat. And on the verifying side, it's, you just verify that everything was done correctly. So that is kind of like how you go from a hard problem, specifically from an equivalence problem, from some mapping, to a signature scheme. Okay. Now, about the timeline. Well, I put in the NIST standardization timeline because it is the most famous, let's say, standardization process. And the way that this works is that, in the fall of 2016, they put out a call for proposals. Okay, so just ask for people to submit schemes, and that might be chosen for standardization. And then we went through 3 rounds of, assessing the security of those. Some schemes go to the next round, some are broken, some don't go to the next round because, they're not compact enough, so on. And we went through 3 rounds first, and then at the end of the 3rd round, there were some schemes that got chosen for standardization. So for instance, we had one CHEM, the Crystal Skyber, and then we had 3 signature schemes. So these are, Kyber is lattice-based, and then these 2, the Lithium and Falcon, are also lattice-based, and Sphinx Plus is a hash-based one. Okay, and then the process didn't stop there. We went into a 4th round. Some of the schemes that didn't yet get standardized but are still considered went to the 4th round. And there was also an additional call for signatures because I think maybe NIST believed that we don't have enough variety in the signatures, or because they wanted a multivariate one. But anyway, there was a call for maybe additional proposals for signatures, and that is the thing that's happening mostly now. The more current thing. And these are the proposals that came in for the new signatures. I've kind of made you a table with how they classify in what we've seen today. So which of them are lattice-based, code-based, multivariate, isogenous. This is symmetric crypto in general, not just hash-based. And these are other problems. So for instance, some, for the min rank, I didn't, allow myself to classify them, but some of them might go into these other categories, but they're considered other. Okay, so finally, why so much variety, right? Why all of these schemes? Well, for that, I need to tell you about the challenges, right? Because our first, as I told you, it is very challenging to find something as good as the discrete log. Okay, we have all of these primitives give schemes that are not so compact. They have huge, either public key secret. We don't have a good substitution for everything. We have schemes that are good for use cases, for some use cases, schemes that are good for others, but not something that is good for everything. And the biggest challenges are, let's say, first we start with the security assessment. So it is a lot of new problems sometimes it's very old problems, but they have some added structure to make them smaller. So then we need to thoroughly investigate the security of this, and that is kind of like a big challenge. Specifically, it has that even some schemes get broken, even severely broken in the later rounds, in the 3rd round of the competition. And here are 2 examples of those. For instance, here it was a case of a scheme that is based on something that is still being secure, the UOV, but it had a lot of added structure to make it smaller. Here it is a case of another challenge that was, that we responded to. For instance, it's a scheme that is also still based on a problem that is hard, the isogeny pathfinding problem, but with added structure so that you can make key exchange, which is something that we cannot do. And then even beyond the security, then the next, why do we do all of these things, adding structure and so on? It's because it doesn't fit. So everything that we have in post-quantum crypto doesn't fit with our current infrastructure of the schemes that we have, so the TLS packets and everything that we want. And also another very big challenge that we're currently working on is this physical security assessment. So what I mean by this is if you assess the security of embedded devices, right, and then you give the assumption that the attacker has physical access of the device, so they can do, they can do some measurements while the device is computing on sensitive data, measurements like time or, the temperature and stuff like that, and then try to infer something from it. So this is a completely different thing. Even if your scheme is secure, it might not be secure when you have access to the device. And this also makes things more challenging because it fits even less on these devices. And then finally, also we have this challenge of building the advanced constructions that we just cannot do because we don't have the discrete log anymore. So that's also kind of very hard. Okay, so I hope I spent this time telling you what we kind of do every day and what's happening in post-quantum crypto. Thank you for listening. And so now I will take some questions if you have some.
Thanks a lot for the talk. I think we have time for a single question that does not take longer than a minute to answer. I think we have exhausted our audience.
Yeah, they're waiting for drinks. We can also, there's someone there. The last one of the event.
So you're saying we have to do all these other things because it doesn't fit.
Yeah.
So we're all really simple. I got to ask them what are they going to put cables in the packet speaker?
Yes, so that's why I said there are some use cases where you can choose that I want top security, I don't care how long it takes, and then you can use something like classic McAleese or, something that is big but is secure. For some use cases, you just can't. I mean, you can, they switched around the TLS to make things. Yeah, imagine a server that gets a lot of requests, so there's also computational time, and these devices, these embedded devices, they're also like very small, so it is an added cost. It's not impossible, but it is an added cost for companies, for everyone, and it just makes things less possible. And we're used to having it good with the program.
This would be way more complicated to do.
Few gigabits more, that is yeah, a lot. Yeah, but well, it depends on what you need, right? It's yeah, it is a lot more in terms of the 10 times more than a elliptic curve case. I don't know, but yeah, we're trying to make things practical. It's always between practicality and security, of course. And if something is too slow or companies find that very costly, they just won't implement it. And we want crypto to be not just secure, but also implementable so that people will actually use it.
Thanks a lot.